All right, so in this video, we're going to talk about substitutions and multiple integrals. And before we get to that, it's probably best to just revisit something we learned in Calc 1, that in which if you understand it, it's going to make the transition into multiple integrals much easier. So let's just take a single integral from Calc 1 from 2 to 3, x root x squared plus 4 dx. Now, we all know by now that this would be a u sub. We would let u equal x squared plus 4, du would equal 2x dx, and then in moving down to the next step, we would have this 1/2 integral u to the 1/2 du. Now, we've mentioned many times in Calc 1 that these values right here can't come down here now that we've changed from x's to u's. And so I've emphasized quite a bit with multiple integrals that these numbers here always reflect the differential. So those are x's. This is an x equals 3, this is an x equals 2. They're not u's. So in Calc 1, what we did is we went ahead and we reevaluated. If x equaled 2, that implied u equaled 8. By taking the 2, plugging it in there, it spits out the u. In a similar way, if x equals 3, then u would equal 13. So these two numbers now can be placed here and here. And if you think about what those numbers represented, that was the interval. So area under this curve on this interval is now equivalent to area under this curve on this interval. So our regions of area, and at least the way they look, have changed. And so that's what we're going to be doing now with multiple integrals. With multiple integrals, we're going to sometimes have functions here, we'll have constants from time to time, and those regions are going to change. And many times the regions that they change into will be much easier to integrate under, much like has been the case from Calc 1. Okay, so to give you a better idea of what this looks like now in what we're dealing with, we'll take a look at this example here where r, which is again our focus now, we're not really focusing on the function itself as much as we are r in these setups. So the r is going to be bounded by these four curves, and we're focusing in quadrant 1. So that's going to look something like this. Well, we know that this guy is the same thing as y equals 1 over x, and this is the same thing as y equals 3 over x. So when I actually want to come through and graph this now, it's probably just going to be easiest to view this one as your y equals 1 over x, and this one as your y equals 3 over x. And then both of these are going to be hyperbolas. The first one here that I'm going to sketch in might look something like this, where that's going to be the x squared plus y squared, minus y squared, minus y squared equals 1. And the second one that I sketch in might look something like this, where we have the x squared minus y squared equals 4. Now, clearly I haven't gone into a ton of great detail with those because we're just focusing on this region here. And so the region that I've got right here, this would be our region R. Now, you can see by setting up an integral and integrating over it, it would be a very tedious process. In fact, you would need multiple setups here for something like this. However, if we go ahead now and we move forward by saying let u equal xy and v equal x squared minus y squared, then it's going to be pretty apparent that if xy equals u, then xy, being u, is going to be equal to 1 and 3. So we can now say u equals 1 and u equals 3. Similarly, x squared minus y squared would now say v equals 1 and 4. So v equals 1 and v equals 4. If I sketch this now, I'm no longer in the xy plane, but I'm in the uv plane. And my u's range from 1 to 3, and my v's range from 1 to 4. Now it looks like what we have, instead of a really messy region here to set up, we have actually a rectangle with all constants. So this guy here would be our new region. Maybe we'll call it S. Now, To be fair, picking these substitutions sometimes is difficult, but as you'll see, many times they are in fact given to us for convenience sake. But regardless, if we're able to take something like this and transform it into something like this, it really does make what we're trying to accomplish a lot easier. All right, so now that we've changed regions, this is where that distortion factor comes into play. That additional r you saw in polar and cylindrical coordinates for the dv, and the additional rho squared sine phi that you saw for spherical coordinates. And we'll touch on that briefly here throughout this section as well. But to take into consideration the change of region, we're going to need the Jacobian. The Jacobian is going to allow us then to change the region and still get the same answer. And so the setup is what do you see on the screen here. Some typical notation might be j of uv. And then we've got partial x, partial u, partial x, partial v, and then partial with y's down here, u's and v's. So the notation that you'll sometimes see as well would be partial xy over partial uv. So these two things are the same, kind of just depends on the textbook you're looking at, but essentially that's what you're dealing with in terms of u's and v's. So then when it comes to computing an integral using a substitution, we'll go ahead and say we're starting with the double integral over region R, f of xy being our function, dA. And I'm going to put a little subscript down here, xy, meaning that's some combination of dx and dy. This now, using our substitution, is going to be double integral over that new region S. If you remember from the last picture, I changed from R into S. Our function now can't have x's and y's anymore. It's a function of u and v. So x will have to be a function of u and v, and y will have to be a function of u and v. Then we're going to multiply by the absolute value of the Jacobian. That would, again, in cylindrical and polar coordinates be that r. In spherical coordinates, it would be the rho squared sine phi. And then we'll have our dA, and that's going to be some combination of du, dv. So that's going to be our setup now when we want to change variables. We're just going to have to remember we need to be with respect to u and v all the way through, here and here, and then we'll also have this additional Jacobian next to it.